Hey there, everybody who's out there already signed in and ready to go. We're going to be starting our webinar in about 9 minutes. 9 minutes. So sit tight and make sure you have a pen and pencil and a pad of paper ready so you can take some notes. And we will be ready and raring to go right at the top of the hour, which should be in about 9 minutes.
And so you cry a little bit to be in love. Oh, cry a little bit to be in love. Day and night, night and day, it hurts to be in love this way. How long can I exist? Falling with I've never kissed. She is all her kisses. What else? She thinks I'm just a friend, though it hurts I must pretend. The only way to keep her is to myself. And so I cry a little bit to be in love. Oh, I cry a little bit to be in love. Day and night, night and day, it hurts to be in love this way. And so I cry a little bit to be in love. Oh, I cry a little bit to be in love. Day and night, night and day, it hurts to be in love this way. It hurts to be in love. Day and night, night and day, it hurts to be in love. Night and day.
About 5 minutes to go, folks. 5 minutes to go. A couple more Gene Pitney songs before we get there.
When you're young and so in love as we, and bewildered by the world we see, why do people hurt us so? Only those in love know what a town without thee can do. If we stop to gaze upon a star, people talk about how bad we are. Ours is not an easy age. We're like tigers in a cage. What a town without pity can do. The young have problems, many problems. We need an understanding heart. Why don't they help us? anything survive when these little minds tear you into? What a town without pity can do. When Liberty Valance rode to town, the women folk would hide. They'd hide. When Liberty Valance walked around, the men would step aside. Because the point of a gun was the only law that Liberty understood. When it came to shooting straight and fast, he was mighty good. From out of the east a stranger came, a law book in his hand. Oh man, the kind of a man the West would need to tame a troubled land. 'Cause the point of a gun was the only law that Liberty understood. When it came to shooting straight and fast, he was mighty good. Many a man would face his gun, and many a man would fall. The man who shot Liberty Valance, he shot Liberty Valance. He was the bravest of them all. The love of a girl can make a man stay on when he should go. Stay on, just trying to build a peaceful life where love is free to grow. But the point of a gun was the only law that Liberty understood. When the final showdown came at last, a law book was no good. Alone and afraid, she prayed that he'd return that fateful night. Ah, that night, when nothing she said could keep her man from going out to fight. From the moment a girl gets a default grown, the very first thing she learns, when two men go out to face each other, only one returns. Everyone heard two shots ring out, a shot made Liberty fall. The man who shot Liberty Valance, he shot Liberty Valance. He was the bravest of them all. The man who shot Liberty Valance, he shot Liberty Valance. He was the bravest of them all.
All right. How's everybody doing? That was one of my favorites, Gene Pitney, The Man Who Shot Liberty Valance, which was also one of the greatest Westerns ever made. I'm hoping you guys can see me okay. My name's John Barba, and this is the first of what we're calling Taco Tuesdays, not Taco Tuesdays, my friends, Taco Tuesdays. And every 2 weeks, we're going to have a webinar put on by TACO, whether it's the first one every month is going to be residentially focused on the smaller circulators and residential heating systems. The second one every month will be focused on commercial systems, featuring our outstanding commercial training department, made up of Rich Medeiros and Brett Zerba, and they'll be taking you through some pretty cool stuff. We're going to be doing some pretty cool stuff too, just smaller. But anyway, I want to do a quick, just a quick status check with you all, just to make sure. I know we have a lot of attendees here, over 200 right now, and some of you are first timers with us. A couple of things, if you could, on your control panel, there should be a little hand, and that's how you would raise your hand if you had a question. But I want to use this to make sure you guys can hear me and see the presentation. Just if you can do that, just hit that little button to raise your hand. That way I know that at least we're coming through on our end. And I see, okay, Alejandro, Alex, great. Thank you, guys. Excellent, excellent, excellent. The other thing I want to make sure that everybody understands is how to ask a question. You should see on your on your control panel. I think it's a little cartoon balloon with a question mark on it. And if you click on that, you should be able to ask a question, and you type it all in. So I see a lot of guys have already typed stuff in. So if you can just do me a favor, just type in hello, how are you, get on with the show, whatever it is you want to type in, just so I know that you know how to do this. And look at all those people pop up. There's Paul, great, excellent. Phil, terrific, terrific. A lot of familiar names. Welcome back, gents. The topic today is one that's kind of really near and dear to my heart, and that's the truth about variable speed circulators. There's so much out there about variable speed circulators, and myself and my fellow trainers, residential trainers, Dave Holdorf and Rick Mayo, when we go out there in the field, we hear all kinds of crazy stuff. I mean, that people either believe these things do or have been told that they do. And it's as a result, it's no accident I played that song about Liberty Valance, because it just really reminded me of the greatest line from that movie towards the end, after Jimmy Stewart's told the crowd, or told the reporters everything, the truth about who really shot Liberty Valance. It wasn't him, it was John Wayne. And the editor of the paper ripped up the notes, threw them in the fire, and said, "This is the West, sir. When legend becomes fact, print the legend." And unfortunately, I think with variable speed circulators, too much legend has become fact, has been printed as fact. These things are marvelous little pieces of equipment. Don't get me wrong, folks. They're incredible pieces of equipment that can do wonders for a residential hydronic heating system. But they're not magic, okay? Some of the stuff that people have firmly believe that they do, they in fact do not do. So let's take a look at some of those legends and whether they whether they are in fact facts or not. Some of the legends that we've heard, they save energy. Okay, they do. They do. Most people, when asked, they say, well, they save a buttload of electrical energy. They save amazing amounts of electrical energy. Well, there's two sides to that story. Yes, they do save a considerable amount of electricity compared to an 80 or 85 watt circulator that runs maybe 2,500 hours, 3,000 hours over the course of a heating season. How much is that? Well, if you ran, let's say, a Takeo 007, a Grundfos 1558, take your pick. And if you ran that for 2,500 to 3,000 hours over the course of a heating season, that's going to be $30-35 a pump, depending upon what you pay for your kilowatt hour. Can a variable speed circulator cut that down? Oh, absolutely. A variable speed circulator with ECM technology will cut that down. Could be 70, 80, 90%. It depends. But now we're talking about $8 to $10 annually as opposed to $30 annually. That's wonderful. Don't get me wrong, guys. That is absolutely terrific. It's a great savings, but it's not going to change anybody's life. All right. People are saying, oh, I've heard people say it's life-changing. It's going to, just do wonders for your electric bill. You may notice it, you may not. The real thing about electrical savings here, folks, is that in a matter of 2 to 3 years, depending upon which one of these circulators you wind up using, in a matter of 2 to 3 years, the electricity you have saved has offset whatever increased purchase price there may be. And if you happen to live in a state where the utilities are offering rebates on these things, you throw that one right out the window too, because they generally will cost less than a standard efficiency circulator would cost. The real energy savings, as we'll discuss, has nothing to do with electricity, but it has more to do with making that boiler sing and dance and work to its peak efficiency. So just understand why we consider that a legend, because I don't think people think it through clearly enough. They always give me the right flow. I hear this a lot. Oh, I use these. They always give me the right flow. And that statement's about, I'm going to say, 90% true. It's missing 2 words at the end that would make it 100% true. And the 2 words at the end are hardly ever. So what makes this statement true is they always give me the right flow, hardly ever. Some are better at this than others, but they work on performance curves, gang. They work on performance curves, they work on programming, and they work on algorithms. They do not magically always adjust to give you exactly the right flow every moment that you're going to need it. Again, some are better at that than others, but don't be fooled into think you're always getting the right flow. You're getting the flow that the circulator tells you you're going to get, and make no mistake about that. And not lastly, but this one's one of my favorites, and I've heard people say this, you know, as facts. Well, they take the thinking out of it. They do the thinking for you. I find that statement crazy on several levels. First off, it's disrespectful to the knowledge base that we have in our industry. You guys are here because you want to know how they work. You want to put thinking into hydronics. You don't want to take thinking out of it. And it's just patently false. You still have to understand how to size a circulator. You have to understand circulator dynamics. You have to understand how circulators work within the system. You have to understand system curves. You have to understand pump curves. And you have to understand where circulators really do work. Just putting in a variable speed pump does not solve all of your pumping problems. In many cases, folks, it can be the start of some pumping problems. So let's make sure we understand that, and we'll get into that in a little bit more detail as we go along. Some more legends. There's a ton of them, even more legends. I love this one. Push the button and it figures everything out for you. I don't have to do a thing. I push the button and it gives me the right stuff all the time, every time. That is, I mean, that's dope smoking crazy. It doesn't work that way. It comes from auto adapt, and with our new 0018E circulator, something called active adapt. It's not what you think it is. A lot of people think that you push the button and the intelligence built into this thing automatically figures out where it needs to be every single time. And that couldn't be further from the truth. Both of those things do something very interesting, but only under certain circumstances and in certain applications, specifically continuous pump circulation with thermostatic radiator valves, non-electric modulating thermostatic radiator valves. That's when that kind of a control system actually makes sense, and that's when it does what you think it does. And again, it's not designed to always give you the right flow. It is designed to use as little energy as possible. It's an electrical savings device first and foremost. So again, we'll touch on that in a little bit greater detail. And then another one is they're magic. I've got all these things. This is the magic pump. You're going to love this. This is the magic pump. How does it work? It works by magic. Anybody tells you a pump works by magic doesn't really know how they work. All right, that's a dead giveaway. They're not magic. They work on math, they work on programming, and they work on the basic fundamentals of pumping. So once we understand that, we have to understand where these legends come from. Where do these legends come from? Again, as I alluded to, they come from the fact that the people that perpetuate these really don't understand how pumps work. They don't understand the interaction between a circulator and the heating system. They don't understand that once a circulator turns on, it's working on a performance curve, and that performance curve is in charge. All right, that performance curve dictates the flow rate. It dictates how efficiently the boiler is going to fire. It dictates short cycling. It dictates all of these things. It dictates your supply and return system delta T, which affects everything. So these legends come from, I think, a fundamental misunderstanding of system curves, pump curves, and how circulators, in fact, actually work. Okay, so we're gonna take a quick look at how they work and how we size a circulator and how that interacts with the system performance curve on a standard efficiency pump, and then we'll jump into variable speed circulators. A couple of things, a couple of questions right here. Is a PDH certificate available for this webinar? At the end of the webinar, it's from Matthew Hollenbeck. Good question, Matthew. At the end of the webinar, you'll be able to download a certificate that says you attended. At that point, kind of up to you to submit it for your PDHs, but yeah, you will receive a certificate at the end of the program. All righty. Couple people said they were having some trouble hearing the audio, so I'm not sure how that. Let me know if anybody else having. Well, dumb question. If you're not hearing the audio, send me a message. You can't do that. Let me know if you're hearing things okay. It could be someone that maybe hasn't been able to log in appropriately with their phone or whatever. So let me know. Yep. Okay. We got a couple guys that are good, so it's got to be on the other end, I think. Excellent. All right. So where do these legends come from? It comes from a fundamental misunderstanding of pump curves and system curves and how things actually work. On a standard efficiency circulator and on variable speed circulators that are set up in either proportional pressure mode or constant pressure mode for variable speed circulators, delta P circulators, the system works on a performance curve, a pump performance curve, and that curve is fixed, okay? That curve is fixed. So when a system is operating, whether it's a zone valve system or a zone pump system, that system has to work somewhere on that curve, whether the system needs that flow rate and head pressure differential or not. Okay. The picture you're seeing right here is a picture of a system, of a pump curve. That pump curve is the red line. Okay. And we figured those out at the factory. The system curve is that dotted line, and that starts from the bottom left and moves up to the right. It's really what you would consider a hydronic fingerprint, okay? It's the unique DNA of an individual system. A zone pump, if you have one pump per zone, that zone has one system curve, okay? It's a mathematical relationship between flow and head. As flow goes up, head goes up exponentially. It's theoretical, but it's important to understand. A zone valve job will have a whole bunch of system curves, one system curve for every combination of zones that could be calling at a given point in time. For example, a 3-zone zone valve system has 7 different system curves. That's how many different combinations could be running at a given point in time. Let's count them out. Zone 1 by itself, Zone 2 by itself, Zone 3 by itself, Zone 1 and 2, Zones 1 and 3, Zones 2 and 3, and Zones 1, 2, and 3. That's 7. All right. So you've got 7 different system curves, and with a zone valve job, you'll have 7 different points of intersection on that pump curve. As zone valves close, the system curve is going to back up the pump curve. Flow goes down, but as you see in this example, the head pressure differential created by the circulator goes up. If you've ever had a problem with banging zone valves, this might be part of the problem. A steep curve pump, a relatively speaking steep curve pump, like most of your 3-speed circulators out there, the standard efficiency Takeo 0015, the B&G NRF 22, the Grundfos 1558, are relatively speaking steep curve pumps. As zones close, we start intersecting, the system curves start intersecting the pump curve at higher and higher points. And zone valves don't necessarily like to close against that kind of a pressure differential, and they let you know they're upset about it by banging and making noise. It's something that happens. A lot of people say, well, then you got to put in a pressure differential bypass valve to make that not happen. But that's basically solving a problem a couple of feet after you caused it, which doesn't make a lot of sense to me. In that case, use a flat curve pump and don't create the problem in the first place. But different webinar, that's going to be next month. Okay, but system curves mathematically we can figure out. So for example, let's say my heating system was right here. This is the requirement for flow and for head for a zone pump. And I use this circulator for that job. All right, I have to plot out my system curve to see where exactly my system curve and pump curve intersect. I'm going to be flowing way the heck out here in terms of flow, with a little bit more head pressure differential. That's basically how they work. Again, unique for each zone. And the reason we care is what we're showing you right here. And here's a better look at it, okay? So let's say I have a zone, okay, that's let's call this, that's going to be about we'll call it 6.5 gallons per minute, and the head loss is 4 feet. Okay, and I'm going to use a 007, standard efficiency 007 circulator right here. All right, I have to work on that pump curve. There's no other way around it. The system must work at that curve. So all the work I do to figure 6.5 GPM at 4 feet ahead goes right out the window because it's never going to work there. I can mathematically plot out, and a B&G system sizer wheel is a great and very easy way to do this. I can plot out all of these different points, okay, on my plot, and then that stuff you learned in 6th grade that you thought was stupid that you'd never use with charts and graphs, now you use it. You plot it out, draw the line, and the point of intersection is right here. So instead of getting the 6.5 gallons per minute I need under design conditions, I'm pumping at 9.5 gallons per minute, and I'm pumping at that all the time, every day of the year. Okay, that's basically how circulators and systems interact, and there's really no other way around that. They interact in that manner. So we're always working on the pump curve, and in many cases with residential hydronics, we're virtually always over pumping. In my opinion, over pumping is it's a chronic issue in residential hydronics, and the reason it's a chronic problem, a chronic issue, is we don't make pumps small enough really to get down into here. variable speed circulators aren't going to do it by themselves. You need to know what you're doing to get them to that level. But imagine a zone or a system that needs 6.5 gallons per minute, and I'm giving it 50% more. I'm up at 9.5 gallons a minute. What's that going to do to the delta T that the system is operating at? It's going to make it get smaller. And as delta T's get smaller, I'm sending warmer and water, hotter water back to the boiler than the boiler's really looking for. I'm going to cause that boiler to short cycle. And a short cycling boiler, as we know, is not as efficient as it could or should be. Here's the thing, guys. No one's ever going to call you up and complain and say, hey, I don't have any heat and it's your fault. You're never going to get that phone call. All right, no one's ever going to call you up and say, boy, my boiler's short cycling a little bit. They may. The phone call you're going to get is 3 or 4 years down the line. Hey, something broke. Maybe we wore out a moving part prematurely. All right, in the combustion chain, and now the boiler needs service maybe before it needed to. Maybe we burnt out an ignition module. Maybe it's an igniter. Maybe it's the blower motor on a mod con. Maybe it's the heat exchange. We've done this stuff, and it's kind of intentionally doing it. Unintentionally, intentionally doing it, I think is probably the better phrase. So does this make sense to y'all? Let's take a quick status check. How are we doing up there, guys? Is everybody happy? Does this make sense? Are we all on the same page here? Okay, going too fast, too slow? Very good. Okay. All righty. Good. Seems like everybody's in a good place. Excellent. Let's move on. Now, when we talk about sizing a circulator, how do we figure out flow? How do we figure out head? Okay, it all starts with a heat load. You got to know what the heat load is. What is the BTU load of the zone, of the house, whatever it is you're trying to heat? What's the BTU load? A lot of ways to do that. Maybe you figure, you do a heat loss, obviously is the right way to do it. Some people, if it's a baseboard zone, they'll measure the baseboard, which sort of kind of gets you there, but really all it does is it tells you how much baseboard's installed, but you got to start somewhere. So let's presume we've done a load on this zone and it's 30,000 BTUs. I'm designing around a 20-degree delta T, meaning the water goes out at 180, comes back at 160 for an average water temperature of 170, or it could be on a low temperature boiler, goes out at 130, comes back at 110 for 120-degree average water, whatever that might be. Industry standard 20-degree delta T. And we're using, in this example, 100% water, no glycol. To figure out my flow rate, I use what's called the universal hydronics formula, which states that GPM, the gallons per minute flow rate you need to heat the zone under design conditions, is equal to the BTU load of the zone, under design conditions obviously, divided by the system's design for delta T times 500. 500 is what we use with 100% water. It comes from multiplying the weight of 1 gallon of water, 8.33 pounds, times the number of minutes in an hour. Traditionally, that's 60, times the specific gravity of the fluid. Water has a specific gravity of 1, times the specific heat of the fluid. Water has a specific heat of 1, because after all, it takes 1 BTU to raise 1 pound of water, 1 degree Fahrenheit in 1 hour, yada, yada, yada. 8.33 times 60 times 1 is 499.8. We'll call it 500. Glycol is going to lower that number a little bit depending upon what you use. There's no industry standardization with glycol, so you got to look at the jug. But the more glycol you put in, the lower that 500 gets. The lower that 500 gets, the higher the GPM is going to be to deliver the BTUs you need. So that's kind of how that works. For our purposes, let's stick with 100% water. So let's put in some numbers. So GPM equals 30,000 BTUs divided by 20 times 500. 20 times 500 is 10,000. 30,000 divided by 10,000, as everybody knows, my flow rate is 3 gallons per minute. So I'm going to need to deliver 3 gallons per minute under design conditions. Okay. As it gets warmer out, that BTU load goes down. Logically, we can say that if the BTU load goes down as it gets warmer out, the required flow rate should go down as well, right? And how do we make that happen? Interesting story. We'll get to that in a bit. So 3 gallons per minute is the flow rate I need. Now let's estimate some head loss. And there's a difference between estimating head loss and calculating head loss. We're going to show you the easy way to estimate head loss. Calculating head loss will show you some surprising stuff here. Estimating head loss always estimates head loss high, okay, at the highest flow rate for any size of pipe. So this is always going to be safe. Sometimes 50% to 100% safe. I mean, you could conceivably double the actual head loss under certain by estimating, but it will be safe and it will get you into a pump. First thing you want to do is measure the run as best you can. All right, you don't have to get in there with a folding ruler and measure every inch of pipe, because then if it's a retrofit, you can't. You do the best you can. You estimate. Okay, maybe I'm going up 10 feet. I'm going over 10 feet. That's 20. It's a 30-foot run down that end of the house, so that's 10, 20, 30, 50. I'm going over 20, so that's 70. I'm coming back 30. That's 100. I'm coming over 20. That's 120. I'm coming down. Whatever it is, you get the idea. You do the best that you can to estimate that measured run. Once you have that number, you want to multiply it by 1.5 to allow for valves and fittings and things. Fittings have pressure drop that are equal to lengths of pipe. For example, a 3/4 inch copper elbow has the same pressure drop as 2.5 feet of straight copper pipe. A 45 has the same pressure drop as 1 foot of pipe. A T has the same pressure drop as 5 foot of pipe, etc., etc. Again, you can't get up there and count them, so you've got to allow for them. You multiply by 1.5. You add 50% to the length. So you measure the run, multiply by 1.5, and then finally, to estimate the head, you're going to multiply what you have left by 0.04. 0.04 represents 4 feet of head loss, 4 feet of head loss for every 100 feet of straight, properly sized pipe at the maximum flow rate for that size of pipe. So for example, if it's a 3/4 inch run, the maximum flow rate I can really run in 3/4 inch pipe is 4 gallons a minute. This is going to estimate the head as if the flow rate was 4 gallons a minute. We know it's 3, but we're estimating as if it were 4. So that's kind of how that works. So we multiply, measure the run, multiply by 1.5, and then multiply by 0.04. Let's go through one. So let's say my total measured length for this little zone is 100 feet. That includes the baseboard, radiators, etc. Total measured length is 100 feet. My first step is going to be to multiply that by 1.5 to allow for fittings. So 100 times 1.5 gives me a total equivalent or total developed length of 150 feet. So if we beat out those fittings into equivalent lengths of straight pipe, it would be a 150-foot long loop. All right, so that's our total developed or total equivalent length. Next, to estimate the head, we're simply going to multiply by 0.04, 4 feet of head for every 100 feet of straight, properly sized pipe. And 150 feet times 0.04 equals 6 feet of head. So what I'm going to need for a circulator is 3 gallons a minute at 6 feet ahead. Now, 30,000 BTUs, I think in most cases, you could look at that and say that's a fairly good size zone. 100 feet total, that's a decent size zone. 3 gallons a minute at 6 feet ahead. And I will tell you right now that 6 feet ahead is overstated probably by 50%. I would guess if we actually sat down with a calculator and figured out the exact head loss through that piping run, it would probably be closer to 3 feet. But again, we're safe here at 3 gallons a minute at 6 feet ahead. Now, what do we do with that number? Okay, all this is building towards what we're going to do with variable speed circulators. But let's put this on a pump curve for fixed speed circulators. All right, a bunch of Takeo 00 series pumps are flat curve pumps. You see the 5, 7, 10, and 12. So 3 gallons a minute right here at 6 feet ahead, here's my requirement. If I were to draw out a system curve, and again, I'm going to estimate here, but if I were to draw out a system curve, it might look sort of kind of like that. All right, it might look sort of kind of like that. So my points of intersection are here, 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 or up here. Okay, so if I use the 005, I'm fairly close, but the trick is finding a 005. It's not a very well stocked or terribly popular pump because it's kind of the 007's kid brother. The 007 is going to be probably your most commonly used circulator in this example, and right now we're looking at probably 3 3/4 gallons instead of 3. Not a terrible overpumping problem, but we're overpumping nevertheless. I got a couple questions here, but I want to jump ahead to the next slide so you can see what happens when we start looking at 3-speed circulators. Again, 3 gallons a minute right here at 6 feet of head. Now, a 0015 standard efficiency circulators, I got a standard 3-speed circulator. Very similar, almost exactly the same in terms of performance curves as the B&G NRF22, the Grundfos 1558. Throw a blanket over them, they're all essentially the same. Now, taking a look at this particular setup, what speed would you choose to run it at? Well, clearly low speed, right? Low speed makes a lot of sense. We might be working right around there, maybe just a shade over 3 gallons a minute. Low speed is actually the perfect speed for this, but we all know when guys use 3-speed pumps, where do they set them? They go right up here to contractor no callback mode. More often than not, if they're not doing the math. And if they go to contractor no callback mode, now I'm running a zone that requires 3 gallons a minute, all right, 6 feet ahead, let's say. But in fact, I'm not giving it that. I'm giving it 5 gallons a minute at almost 15 feet ahead. See, the head's in a zone pump, the head's not going to matter so much, but I got 5 gallons per minute where I need 3 gallons per minute under design conditions. Okay, that's 66% more flow than I need. If I ever see a 10-degree delta T on this job, I'd be surprised. Okay, and when I got a 10-degree delta T, the water may be going out at one temperature, it's coming back 10 degrees cooler or less. What is that boiler going to do? All right, I'll ask you guys, what do you think that boiler is going to do? Chances are it's going to short cycle, and a short cycling boiler, we're going to wear out parts prematurely, and it's never going to be as efficient as it could be. And gentlemen and ladies, this is the best scenario you will ever see, because it's always going to work here. As it gets warmer out, as we said, the BTU load goes down, the required flow rate goes down. All right, so if we spend 50% of the heating season, gang, at 1/3 load or less, 1/3 load is 1 gallon a minute. Even then, I'm giving it the full 5. So just imagine what's going to happen. All right. This is normal, guys. This happens every day, and nobody considers this a problem because no one's ever going to be cold. All right. No one's ever going to be cold. Daniel Leary asked a question. Radiant system loop. Do you measure the length with the measured run? Do you measure the length with the measured run? Yeah. What you do with Radiant is the longest loop length, the longest loop length on a specific manifold, plus the flow rate going through that loop, will give you the radiant head loss. All right, you just pick the worst case one from the manifold, but you have to add into that, Daniel. You have to add into that all of the supply and return piping going back from the manifold back to the pump and from the pump to the manifold, because that's additional head loss. So that's head loss in series. You'll add that, and then you come up with the head loss. Okay. So in a couple things about a buffer tank. Buffer tanks, guys, are fantastic with low mass boilers. Really a great thing. Can help. It's a big help towards this. It's a huge help towards mitigating this. If you were to combine a buffer tank with, let's say, a Delta T variable speed pump, now we have Christmas, New Year's, and a ban on Chinese imports all rolled into one. Okay, all rolled into one. Willie Ham asks, if we're modulating water temperature, do we still need to modulate flow? I think they go hand in hand. One doesn't negate the other. They both go hand in hand. Okay, they do both actually go hand in hand. If you can have the right flow and the right temperature, now we have the right system. Put them both together, the right flow and the right system. Okay, let me know if that answers your question, Willie, and I hope you're doing well. I hope you know, Willie, I'm just down the street from you now. I live in Exeter, New Hampshire, so I'm just down the street from you. All right, a couple other questions. Let me get back up here. Some more questions. Where are they? Buffer tanks work, and buffer tank is a good thing with a high mass boiler as well. It makes a lot of sense. So buffer tank is, to me, if you've got a ModCon boiler, low mass ModCon boiler, and a lot of zones, buffer tank to me is standard equipment. It shouldn't even be an option. It's standard equipment. If you have just a few zones and the smallest zone is smaller in BTUs than the lowest I'm sorry, if the smallest zone is bigger than the lowest firing rate of the boiler, then I think a low loss header or an oversized moose antler kind of primary secondary header will certainly do you. Okay. Quick question on the pump curve. If the system head is below the pump curve, will the flow be as shown on the flow at the system head? No, the flow, again, we got to, if I understand your question correctly, DS, you have it all follows, it follows the pump curve, the system curve. You plot out a system curve. So I think what you're saying is, if I understand you correctly, saying, all right, 3 gallons a minute at 6 feet ahead, is head the limiting factor? Am I going to be working way the heck over here? No, I'm not. I'm not going to be working right here. I'm going to follow the system curve to where it intersects the pump curve. So you got to calculate the system curve and see where they intersect, because flow and head, as flow goes up in a system, as you're pumping more flow through the system, the head loss through that piping system increases exponentially. So you kind of have to do the math to figure it out. And the math's not that hard, but it's just as long as you know that that it works. Is there software to input the numbers? Absolutely, Tony. There's software. Takeo has software that can do that. Bell & Gossett has software that can do that. We're going to show you something actually kind of interesting, though, towards the end of this thing that might help you out. So let's hang on to that, Tony, because something at the end that I think you might find very interesting. So good, excellent, good questions, folks. Good questions, good interactions. Now let's talk about variable speed pumps. We're about halfway through this. We've set the stage. Let's talk about variable speed pumps. And I love the most interesting man in the world. And he doesn't always use variable speed pumps, but when he does, he knows why. He knows why. All right. So let's take a look at why we might consider using a variable speed circulator. And let's look at the variable speed lowdown. And in the variable speed world, we have delta T variable speed pumps. Delta T variable speed pumps have sensors. One goes on the supply, one goes on the return. All right. And it monitors the difference in temperature. And what you can do is you can program it to maintain the delta T in the system that the system was designed for. All right. So if it's designed for a 20-degree delta T, you can sense the temperature of the water going out, sense the temperature of the water coming back, and the circulator will vary its speed to try to maintain that delta T, that temperature differential, which is kind of a slick way of running a variable speed circulator. Okay, because it does wonders about the incredible shrinking delta T, which can help the boiler. And it makes the pump work as efficiently as the pump can possibly work, as well as helping the system work efficiently. That's delta T. We also have delta P variable speed pumps, which are more common primarily because they're less expensive and they're simpler. There's no sensors involved. There's no sensors inside or outside these things on the residential end. They're just simple little circulators that you don't really have to think about. On the face of it, you do really have to understand what they're doing and why, but there's no sensors to deal with. There's no light show on some of them. There's no light show on the control panel. They're very simple and easy to work with. Delta P variable speed circulators will vary their speed to maintain a specific delta P or pressure differential within the system. All right, they maintain a specific pressure differential within the system, or they'll adjust it depending on how it's programmed. It can adjust if you have continuous circulation and thermostatic radiator valves. It can do a different. It does the same thing, only differently. When we're talking about a delta P pump, again, it's going to work based on its programming, and it's generally going to work on a line, on a pump performance curve, as we shall see. And that pump performance curve is fixed. So it's got to work on those lines. Delta T pumps to a degree that line can move as needed, but delta P pumps, again, pressure differential, will move, will work on that one line. They'll vary its speed, but they'll stay on that one pump performance curve, and you'll see how that works in a moment. Think about that. Think about a delta P pump when used as a zone pump. All right, think about a delta P pump when used as a zone pump. The trigger that tells a delta P pump to speed up or slow down, and we'll simplify this. The trigger that tells a delta P pump to speed up or slow down is resistance against the impeller. Let's take a zone valve job, for example. On a zone valve job, as zones close, let's say the impeller's spinning along, having a grand old time with all zones open. A zone closes, okay? A zone closes. All of a sudden, that impeller is spinning against more resistance. It's spinning against greater resistance. That tells the circulator's intelligence, it says, hey, something has clearly closed. I'm pumping against more resistance. I think I better slow down based on my programming. So it'll slow down. Another zone closes, increasing resistance. It'll slow down yet again. A zone opens, less resistance, right? Less resistance in the system, the circulator will speed up, again, according to its programming. Now, think about that when used as a zone pump. Is there anything in the zone that will ever change the resistance that impeller's seeing? And the answer is no. There's nothing in that zone that's ever really going to change much. So when you use a delta P pump as a zone pump, it's not a variable speed pump. It's a fixed speed pump. It's just figuring out its happy spot, and that's the spot it's going to work at. So a lot of people say, well, then that's stupid to use it. That's ridiculous. It's not going to vary speed. Why the heck use the thing? Okay, I get that. But understand this, set it up properly. Instead of satisfying that zone at 85 watts on a fixed pump performance curve, if you know what you're doing with this pump and how to set it up, you might be able to set up a performance curve that's really close to dead on accurate where that requirement might be under design conditions. And maybe, just maybe, you can heat that zone at 17 watts instead of 85. Now we've got a little bit more of an energy saving story to tell here, as well as we're not over pumping like crazy. So both good things. So always think that one through, okay? So that's a bit of a difference there. Again, variable speed solutions, delta P, delta T, they're the same thing, only different, okay? They're similar, actually, similar, only different. Whereas, again, delta P, we watch the, we adjust to zone valves opening and closing, basically, versus delta T, where we adjust to maintain a fixed delta T within the system. Okay, I don't know why that's controversial, but to some people it is. I don't get it. Why delta T? Well, delta T math is why delta T. GPM equals BTUH divided by delta T times 500. Okay, delta T is delta T. That tells you something, all right? In many cases, it can tell you what's being taken out of the system and delivered into the house in terms of energy, in terms of heat being delivered. Okay, GPM, we know when it comes to BTUs, we know BTUs are going to change, right? BTUs are going to change all winter long. The BTU load's going to change whether, based on how many zones are open or closed at any given point in time, okay? And it will also change when it changes with the weather, okay? Your BTU load changes with the weather. As it gets colder out, the BTU load goes up. As it gets warmer out, the BTU load goes down. That's always going to change, okay? If your gallons per minute flow rate is fixed, meaning we're working on that pump curve. If the gallons per minute flow rate is fixed, what does the delta T have to do? The delta T has to change. It has to vary. It has to move. Okay. Flow rate stays the same. The BTU load goes down. The delta T goes down. So we get, I've had guys say, well, I've been in a mechanical room. I don't know how many times. I've never seen a 20-degree delta T. Yeah, because you got a fixed speed pump running at it's too high of a speed. Of course, you're not going to see a 20-degree delta T. Because as the load goes down, the delta T gets smaller. And if the load here, if the flow rate, if you need to be down here on your pump curve, but you're actually working up here, you're never going to see that 20-degree delta T anyway. You're over pumping right from the get-go. Now, what we can do with a delta T pump, all right? If the delta T is fixed, and we know the BTU load is going to vary, well, the GPM has to vary in lockstep with the load, okay, for as much of the time as we possibly can. We're going to put an asterisk on that because it's not all the time, but it can be, depending upon the system, a heck of a lot of the time. That's the brilliance of delta T, okay? So if the delta T is fixed and the load goes down, the flow goes down along with it, and vice versa, whether it's a zone pump or a zone valve job. Okay, and in theory, what we have is an infinite number of pump curves. So let's take a look. This is the Takeo VT2218. Why do we call it the 2218? 22 here on total feet ahead, 18 gallons a minute down on the other end at max speed. And this is the minimum speed. So I can't go faster than that, and I can't go slower than here. This is my floor. I can't go any slower than line A. So let's take a look. Let's say I have, here's my 2 gallon a minute at 6 feet of head zone pump, all right? What's going to happen is this circulator knows that under design conditions, I need 2 gallons a minute. I need 2 gallons a minute to maintain that. Again, presuming everything is designed dead on accurate, okay? If that 6 feet ahead is dead on accurate, the 20,000 or the 2,000 BTUs, however BTUs I need, that's dead on accurate. I'm going to work right here. This is the maximum speed that circulator's ever going to run. And that may be about 25% of the max, okay? That may be about 25% of what we have up here. That's the speed it's going to run under design conditions on the coldest day of the year. As it starts to warm up, this line is going to move down because I don't need as much flow because I don't need as many BTUs, right? It's getting warmer out, the load's going down. So this line is going to go down until I hit that minimum. And when I hit that minimum, that's where it works. It's no longer a variable speed pump, but it is at that point a 9-watt pump. Now you're heating the house with 9 watts, okay? So in a zone pumping application, that's kind of where it makes some sense, all right? So let's take a look at, if I were to do this with, let's say, a zone valve job, and let's say it's 7 gallons a minute at 6 feet ahead, all right? I want to be right here, 7 gallons a minute at 6 feet ahead under design conditions. As zones close, let's say my smallest zone is 2 gallons a minute at 4 feet ahead right here. As zones close under design conditions, the speed's going to drop like so. This is my speed under design conditions with my one smallest zone calling. This is my speed under design conditions with all zones calling. Again, as it warms up, both of these lines are going to drop until I'm going to wind up probably spending at least half of my heating season running as a minimum speed 9-watt pump. That's just the way it is. Okay, so that's kind of delta T in a nutshell. Let me grab a couple questions here. Would it be a good idea to use a delta P pump as a primary pump? This is where we start getting a weird terminology. With a cast iron boiler and a primary loop, yeah, I'd say so. When you're talking about a boiler pump for a modulating condensing boiler, I'd run that past your boiler manufacturer because they have very specific requirements on what they want for flow through that heat exchanger. They don't necessarily want to vary the flow. They want to scrub the heat exchanger BTUs. So Roger, that's when always run that past your boiler manufacturer and ask what they recommend. Okay. Don Cottrell asks, what is the programming telling the intelligence the resistance? Is it measuring power consumption and using affinity laws to relate that to pressure? More or less. It's basically interpreting amp draw. All right. As far as the actual programming from it, I'm a guy who knows my limitations. The actual math behind it, it's out of my world. But basically, the algorithm is interpreting the amp draw into resistance, if that helps you. Okay. All righty. Let us continue. Adjusting, changing pressure differentials. Delta T pumps getting some blowback on supplyhouse.com. Don't know much about that, Jeff. I do know an awful lot of people use them and like them a lot. It's not a perfect pump. It's a pretty darn good pump, though. It does a lot of interesting things. So where supplyhouse.com is coming from, couldn't tell you, don't know. I do know it's not a lot of people say, well, which pump should I use when? And I don't think it's a matter of Delta P's best in this application, Delta T's best in that application. I think it's a measure of degree. In my opinion, Delta T pumping properly applied is always a better choice, but in some case, as a better choice, it's a lot better. Some cases it's a little better, and in some cases it's really no difference. All right, it depends on the size of the system. The smaller the system, and quite frankly, most residential systems, we're talking on the smaller end, the difference is not as great as you would think. Okay, so I think you can certainly, in my opinion, if you held a gun to my head, I'd say, Delta T is a superior way to run a pump. In some cases, it's a no-brainer, so far superior, it's not even funny. In other cases, it's a little bit better. In some cases, there's really no difference at all. So let us continue. Yeah, I've heard about the buzzing sounds. I've heard about that in some of the older ones that we have seen, some of the first ones, but that's kind of been licked from what I've heard, that was licked quite a while ago. But yeah, a couple of the early models, we had some buzzing sounds. We figured that out. Okay, it's annoying. It is an annoying sound. The bumblebee, again, I lived with a bumblebee for like 8 or 9 years, and it never made a sound for me. But other different models, they had some issues with that. That's one of the things we work towards changing as we develop new pumps. So I'm hoping that answers your question. Again, delta P adjusts to changing pressure differentials, less expensive, no sensors to deal with, which people kind of like. All right. It varies its speed, but again, that performance curve is fixed. And let's take a quick look. This is the 0015 E3. It's kind of like for people who like 3-speed circulators, we have a 3-setting pump. All right, low, medium, and high. You like 3-speed pumps, this thing's going to give you, it's going to address the shortcomings of 3-speed circulators when used in a zone valve job. Because think about using that kind of a pump curve, ultimate flat curve pump, instead of something up here to keep zone valves from banging. All right, that makes sense. So it gives you the ability, if you know the flow and you know the head, especially on a zone valve job, but also on zone pumping applications, to be able to get your performance curve as close to the requirement as you need. All right, it's getting there as close to that requirement as you need. Let's take a look. That zone pump we had earlier was 3 gallons a minute at 6 feet ahead, right? It was 3 gallons a minute at 6 feet ahead. If I'm looking at this 5 foot ahead setting at low setting, the low setting's 5 foot ahead, that looks like it might be a little bit less, doesn't it? It might be a little bit undersized. But remember what we said earlier about that measure the length, multiply by 1.5, multiply by 1.5, then multiply by 0.04, will almost always oversize your circulator. I'm looking at this and I say, you know what? That's where it says I need to be, but I've got this line right here. You know what? I am happy to set that pump at the 5 foot ahead line. So so I'm really going to work right about there. Okay, really going to work right about there. Think about under design conditions, how close I'm going to be to the right size. So I may not have a 20-degree delta T, it might be 19, 18, 17. The point is it's not going to be 10, okay, which is a hell of a lot better. It's a hell of a lot better. All right. As it gets warmer out, again, what I would do is simply follow the system curve. As it gets warmer out, I'm going to need to be down here, or I'm going to need to be down here because the load is less, therefore the flow is less, and it'll work on the system curve. I'm still going to be operating up here. So my delta T is going to go down. Okay, my delta T is going to go down. Nothing I can do about that. Nothing I can do about that. But as a zone pump, I'm working right here. Maybe that's 17 watts instead of a typical 3-speed circulator where I might be running at 80 to 85 watts. Okay, that's going to make a big difference. Want to make sure that that part is clear to y'all. Now, again, for zone valve jobs, let's say I had 7 gallons a minute at 5 feet ahead. This is where I want to be with all zones calling. All right, I'm simply going to be working right along this performance curve. As a zone valve closes, I'm going to intersect here. I'm going to intersect here or here or here, and my electrical consumption is going to go down. How does it do that? Let's take a look. I'm going to skip through this one because we already did that one with the zone valves on the delta T pump. But this is how we work with delta P constant pressure. Now, what you have in a delta P pump, you have a cajillion of these independent, separate pump operating curves, okay, that are programmed in. They start here at minimum speed, they go up here to max. There's a ton of them just programmed in here, all right? Let's say for giggles and grins, I've chosen the 10 foot of head constant pressure setting. System curves and pump curves still apply here. There's no difference. I want to be here, but I'm really working here, and I'm working on that performance curve, okay? Now, let's say a zone closes. Even though I want to be down here, I want to be 7 gallons a minute at 5 foot ahead. I'm really at what? I'm going to be about 8.5 gallons a minute. Let's look at it that way at 10 feet ahead. I have more flow than I need. Delta T is going to be smaller, but it is what it is. Now, when a zone closes, what's going to happen is it's going to act actually like a regular pump for about a nanosecond. As a zone closes and I have a new pump curve, as a zone closes and I have a new system curve, it's maybe working up here and intersecting right here, my operating point is going to go up here for like a nanosecond. It's going to sense that extra resistance, interpret it in terms of amp draw, and then boom, drop right back down to that 10 foot ahead. So it's going to play out like that. okay? But really what it's doing is this. It's going up and then down. Same thing here. I got a new pump curve. It's going to go up and then down like so, okay? Next one, up and then down, okay? And if you watch it on a wattage gauge, it's kind of like a blip, up, goes up just a hair and then goes right back down to the wattage that it needs. So as we're going down in pump performance curve, we're going down in speed, we're going down in electrical consumption. And here's a kind of a graphic illustration of the same thing. Okay, so out here maybe I'm at 44 watts. It's a maximum 44 watt pump. A zone closes, I'm now down to 30 watts. Another zone closes 23, another zone closes 17. Okay, and that's kind of how that works. All right. So a couple questions in here. Benjamin Avery asked, which would you use on a boiler with outdoor reset? Again, I would say as a boiler pump, I would use neither. I'd use the pump that the boiler manufacturer tells me to. For my distribution, whether it is for a zone pump application or a zone valve application, Benjamin, again, I'd use either one depending upon which one makes more sense. The bigger the system, the more benefit I'm going to get from a delta T pump. The smaller the system, the difference starts to kind of fade, and now it becomes a how much does the pump cost kind of a question. There's no one that's right for the other. A lot of folks think, well, delta T, that's going to fight the outdoor reset. Delta T couldn't care less what the water temperature is going out to the system. It only cares about the difference between what's going out and what's coming back. Okay, does that make sense? Let me know if that answers your question. Okay, let's take another look at a couple of other questions here. I had another one from Willie. Where are you, Willie? I had a question here from you. Where is it? There we go. My idea about delta T on a multi-zone zone valve system is that you're measuring a blend of zone delta T's, which may not give the best performance for every zone. Absolutely correct. We're not going to have a 20-degree delta T in every zone. What we're going to have is a 20-degree delta T for reading what's going out to the system and what's coming back to the boiler. You're going to have the exact same problem. You're not going to have the best delta T in every zone with a delta P pump either. It's not or a standard pump. You're not going to have. You're still blending them all. If I'm understanding your question correctly, Willie, regardless of what pump you use on a zone valve system, you have the same issue. Okay, you're going to have different delta T's on each zone coming back. That's just the way it is. Which reminds me of another one of those legends I heard. I heard some guy say, I use delta P pumps on zone valve systems because I don't have to make my zones the same length. The pump will make up for differences in zone lengths because it's pressure regulated. To which I say, what the heck are you talking about? I don't understand. That makes absolutely no sense. The pump cannot possibly make up for differences in zone lengths or loop lengths on a radiant system. It just doesn't do that. Okay, so let's see how we're doing. Here we got more questions. Can you use a 0015E on a variable speed injection system? Really, you want a fixed speed pump with a variable speed injection controller, because what variable speed injection controllers do, Darren, is they chop the sine wave, which is an alternating current thing, and these are DC motors. So you don't want to use any on an variable speed injection mixing system. You want to leave her alone. Just again, a regular pump, and then a regular circulator, standard efficiency circulator, and let the controller vary its speed, if that makes some sense. Okay, now let's talk Bluetooth. I got about 5 minutes and I want to make sure I get this in. Let's talk Bluetooth and the 0018E. We talk a lot about accuracy and making sure we got stuff right, etc. Well, what we've done with the 0018E, and this pump's been out almost a year now, is we've added Bluetooth technology to connect to an app on your smartphone or tablet. And what that app does, it's not just a cutie pie thing. It's actually a tool that allows you to fine tune this system about as well as it can be fine tuned. And all you have to know, whether it's a zone pump or a zone valve job, all you have to know is the flow. All you have to know is the flow, and that's kind of cool. Let's take a look at this. And I know I got a lot of questions here, guys. Soon at the end, we'll go through all these things and make sure we have it. App-based control. What you have here is a multifunction delta P pump. It works on constant pressure for zone valve applications. It's an infinitely variable fixed speed setting as well, so for zone pumping applications. So you have those choices. It can do either or. If you have a constant circulation proportional pressure type system for where this pump is suitable, then you can use proportional pressure, constant circulation with thermostatic radiator valves, or you can use what's called active adapt, which is what it sounds like. You press the button in a constant circulation system with thermostatic modulating radiator valves. It will find where it needs to work if you give it enough time, So let's take a look at what this thing can actually do. And really what it does, and I stole this from Dave Holdorf, is it allows you to see inside of the pipe. You can actually see what's going on inside of the system. It gives you, the app gives you a window, gives you the hydraulics of the system. Where am I really flowing? What is the head loss here? Where do I need to be? It helps you find all that stuff out. And allows you to adjust this circulator about as well as a circulator can be adjusted if accuracy is your goal. So I've got two-way Bluetooth communication. I don't need it. I don't need Bluetooth to make this thing work. I can set it up using the dial and just forget the app altogether if I choose to. But the app really makes this pump sing and dance. I've got the 4 different options. Once I get into Bluetooth on my app, I can see these different performance curves and different programming. I have infinitely variable fixed speed. I have 9 constant pressure settings. Whereas like the 0015E3, I had 3 settings, low, medium, and high. Here I've got 9. I've got 9 proportional settings for those thermostatic radiator valves, and I have active adapt for those thermostatic radiator valve applications. So let's take a look at how this works. For my infinitely variable fixed speed, all right, basically what I have, if you see that slider up on the top of that picture, I have a slider there that will allow me to set it. Hey, you know what? I got a video. Let's show you the video here, okay? This was just a video taken of the app, a screenshot off of my app. And what we're using here is the demo mode. So it's in demo mode on the app. So, and you can download this app, go to the App Store, just Takeo ECM pump, and you'll be able to download the app and try the demo. So let's hit the demo. All right, and here you can see I'm starting out in my blue mode. That's my zone circulator. That slider up there, which is 100%. With your finger, you can move that ball back and forth, and you'll see the ball move where the system's actually operating. And then down below, you see the flow. I just went from 7 to 3.5 gallons per minute. You can see the head, 12.96. I'm moving it again. Now I'm over at 5.69, 10 feet ahead. As you adjust the speed, okay, of the pump, you move the flow and head. All right. So think about this when you're sizing a zone pump. You don't have to pick a pump curve. All you have to do is know the flow rate. And really, to figure that out, all you need to know is the BTU load. So again, if it's a 30,000 BTU zone, that's 3 gallons a minute, baby. I go back here. I move with my finger. I put my finger on that slider on that ball. See where it says 71%. I put my finger there and I just slide it until the ball down on the blue pump curve area. Okay, you'll see that pop up right there. I move it until that thing gets down to 3 gallons a minute. It'll tell me the head. All right. I don't need to program anything for the head. It'll tell me the head. All right, but I'll be at 3 gallons a minute. And I do it simply by manipulating the manipulating the slider on the app, and I program that circulator as well as it can be programmed. Okay. Now, if it's a zone valve job, I can use this. I can actually use the blue mode to start with my zone valve application. If I know the total flow for my zone valve system, let's say it's 70,000 BTUs. Okay, that's 7 gallons a minute. What I'll do here is I'll start in the blue mode. I'll adjust my slider until my dot, this guy right here, until that dot is at 7 gallons a minute, which would be right about here, is at 7 gallons a minute. Then I look down at the bottom right here. It's going to tell me the head. Then at that point, I know the flow is 7. The app has told me the head, and then I go to my constant pressure zone valve setting right here. And simply by pressing the line that I want, I can pick the constant pressure setting that I'm looking for. So it might wind up being that one. Okay, here's your proportional pressure setting. Again, you touch the different lines and it'll adjust to the one you want. And thermostatic radiator valves. And then active adapt, you simply press that and let it run. It's going to take about 90 minutes to 2 hours to kind of figure out where it needs to be. It's really for continuous pump circulation only. It's not a zone. It doesn't. A lot of people think I press that button, it does a complete system analysis and figures out exactly where it needs to be and constantly readjusts every time the thing comes on. Not even close to what it does. It's got to run and run and run to figure out where it needs to be. Okay. Lastly, there's also a diagnostic setting here. You get the total number of run hours. You get the number of shutdowns, basically cycles. How many times is this pump turned on and off since I installed it? Helps you figure out if you've got a short cycling problem still. Maybe we didn't optimize the setting. Tells you continuous overall energy consumption and alarms. Have we had to go into all of our pumps have what we call sure start. If you ever get a locked rotor situation, it'll unlock itself. If you ever get if the pump is ever airbound, it'll automatically purge itself. This just tells you how many times that's happened. And it's cumulative. Every time you log into a specific pump, man, you can check it right out. Alrighty then. That ends the official program. I appreciate you guys hanging out here. We've still got a lot of questions. So let's go to those. All right. And I'm going to do something kind of crazy here. Let's see if we can do this. Webcam. Let's have a little bit of fun. All right. There's the webcam. How you doing all? Good to see you. Let's go through some questions here. All right. Let's do some questions. Well, first one's an easy one. Are you going to be in Orlando for the AHR Expo? Absolutely. Absolutely we will be. Come see our booth. We'll have the 0018E there. You can check it out for yourself, as well as everything else we have. So we'll look forward to seeing you there, Daniel, and stop by the booth on Monday because get an invitation to our party. Will this training be archived for future viewing? Asked Eric. Absolutely, yes. It is being recorded. Tomorrow you will receive an email, follow-up email, just thanking you for attending, and it will give you a link for a link to the recording of the webinar. The recording will also be archived on the TACO website, so you have both of those options available to you. Okay. Let's see what else we have here. But would still like a certificate. Yeah, Ernest, when you log off, you'll be able to. They'll ask you if you want to download a certificate, so you can simply download it from there. Matthew Vangel, looking at replacing all circulators with Delta T pumps after baselining each zone independently, adjust each 0015-3 based on ideal Delta T range. There's a question in there. I'm not sure if there's a question you're asking there. If you could let me know. I'm not quite sure I understand. So let me know where you're at there, Matthew. Oh, maybe there's another question here. Can you adjust the Delta P pump speed based on? Can you adjust the Delta P pump speed based on a stabilized Delta T? If the Delta T is low, do you raise the speed? Actually, it's the other way around. If the Delta T is too low, you want to lower the speed. All right. Okay, lower the GPM, the Delta T will go up, if I'm asking right. Basically what you would do, the way you program a Delta T pump is you pick the Delta T that you want for this system. What was the system designed for? Typically it's a 20-degree Delta T, and the pump actually comes out of the box programmed for a 20-degree Delta T, but you can change it anywhere from 5 to 50. But you start out when you install it, says what's the Delta T I want to see in the system under design conditions? If it's 20, you put the sensors on and it'll work on a 20-degree Delta T and constantly change. Once you hit that minimum speed, however, it's a fixed speed pump. So the Delta T, as the load goes down, the Delta T is going to get smaller, and there's nothing you can do about that. The point is it might be a 17, 16, 15-degree Delta T instead of a 4 or 5-degree Delta T, which is better. Okay. Good questions, guys. Good questions. Are the ECM circulators drop-in replacements for older pumps, flange to flange length? Yes. The 007E, the 0015E3, the VR1816, the 0018E, and the VT2218. Same flange to flange as our standard 00 series line, Mark. So I hope that helps you out. Good question. Okay. Let's continue. I'm scrolling down here. How will this pump work in domestic hot water? Good question. Domestic hot water recirculation. We have a DHW pump called the 006E3, which is an infinitely adjustable fixed speed pump. You can adjust it to whatever speed you want. Okay. that is needed for the application, and it will use the appropriate amount of electricity. It'll be a fixed speed pump at that point. Again, I see a lot of people think, oh, this domestic hot water pump has auto adapt / active adapt. I press the button and it'll figure out exactly what it needs to do. No, it's designed for heating systems. It doesn't do anything there. What you want to do is figure out what speed pump you need for domestic hot water recirculation and let it go. ECM makes a lot of sense in domestic hot water recirculation because theoretically those are going to run more over the course of an entire year. All right, you might have one running, you know, a few hours over the course of every day. It's going to add up. Okay, so you might want. And some people, unfortunately, when it comes to domestic hot water recirculation, and this is going to be in our March webinar with domestic hot water recirculation, what they'll do is just turn the pump on and let it run. Hey, to hell with it. You know, we just want people to never have a problem with hot water, so the pump's going to run all the time. Okay, that's fine. That's fine. Better to use an ECM pump for that than anything else. The problem is you got a pump running all the time when maybe you don't need to. And we'll talk in March about some smart ways to deal with that. So I hope that answers your question, Alexander. That's a good one. Okay, a couple of others. Let's see. If my air temp and water temp are constant, why would the flow requirement be reduced when it's warmer outside, Frank? Because GPM equals BTUH divided by delta T times 500. That's the law. Okay. GPM equals BTUH divided by delta T times 500. What makes BTUH change? The weather. All right. The weather makes it change. I don't always need 30,000 BTUs in a zone. Okay. I just don't. I don't. So if I can lower my flow rate to match that, I'm going to have longer run times. Is it better to have 2 10-minute run times or 10 2-minute run times? You tell me. Okay. All right. These are great questions. These are great questions, guys, and I really appreciate them. I really do. This is terrific. Let's go back up here. A bunch just came in. Stainless steel available. Stainless will be coming out in, yes, those are going to be coming out over the course of the year for the 0015 E3, and I believe the 0018. I'm going to have to check on that. Rick Mayo, you're online, and you let me know. I see, is the 0018 E coming out in a stainless steel this year? I'm not sure it is. Is the 006 E3 a bronze pump? Asked Jerry Hogan. No, it actually has a composite body with union connections, okay, for residential applications. But we will be coming out with stainless steel flanged ECM pumps. Yes, we're talking about the 0018E, so yes, that we've been told that will be coming out this year, along with the 007E and 0015 E3 in stainless steel, okay. So very good. Yeah, it's a half union connection on the 006 E3. Okay, a couple another one. Replace the 007E with what if the temp controller delta T cannot be reached due to a low BTU load with a buffer tank? Is there any way to get more support on this issue? Replace 007E. Jeff, restate that question for me if you will. Can I? If it's a low BTU load, again, delta T pump, like I said, it's got that minimum speed. If I'm understanding your question correctly, Jeff, if you're below that minimum speed, it's a fixed speed pump. It's going to act like a fixed speed pump. All right. If your requirement's below that fixed speed, your delta T is not going to be 20. It's going to be something less. If that's the question you're asking, so let me know if that's the question you're asking. Nice question from Bruce Marshall, the smartest man I know. Does Taco still make regular pumps? Yeah, we do. Yeah, we do. We still sell quite a boatload of 007s, of 008. You know, our standard efficiency circulator is still a thriving business. So yeah, we have those. Oh, and Rocky Pavey was about to take off. Rocky, thank you. I still have your mug here. Dan Silvestri, I don't see your bumblebee and boiler piping set up in your basement. That's because we moved, Dan. We moved from Minnesota to New Hampshire. So I live in New Hampshire now. And this is my office at my home in New Hampshire. So it's no more boiler room, unfortunately. I should have taken a picture of it, made a big backdrop here. All righty. Very good. Very good. 38 below in Alaska. Oh, my goodness. That's kind of nuts. Let's see what else we have here. But a lot of good questions, guys. Thank you. Let's see. Let's move on up here. Can you use a 0015 on an inject? Oh, no. So we got to go back down that way. Here we go. No, let's see. I'm losing some questions here. Okay, what do we have? Do you recommend a buffer tank on all installations? It's never a bad idea, man. I tell you, it's never a bad idea. I think the rule, and I learned this from my good friend Anthony Reichow, if the smallest zone, the BTU load of the smallest zone on your system is lower than the lowest firing rate of your ModCon boiler, then yes, buffer tank, absolutely, absolutely. Excuse me. Hold on. There we go. Oh boy, yes. Oh goodness. I made it through the whole thing. The dogs didn't bark this time either. Back to your question. I'm gonna try and make it, guys. Now I gotta find the question. Where was it? If the boiler, I'm sorry, I'm gonna come back to your question. Here we go. If the BTU load of the smallest zone is smaller than the lowest firing rate, always use always use a buffer tank. If they're about the same, hydraulic separator is a great idea. There are a lot of good ones out there. If it's one or two zones, and both zones are way bigger than the lowest firing rate, you can make us do a standard moose antler primary secondary branch with a ModCon boiler, and I think you'd be fine. Oversize the header a little bit, but I think you'd be fine. So that's kind of the way I look at it. So it's never a bad idea, but if you got a microzone system, a lot of zones like you might have with a radiant system, buffer tank is a fantastic idea. If you have a boiler that's short cycling, will lowering the delta T fix the problem? A lot of things go into short cycling. I think maintaining a delta T, and again, a wider delta T. Again, most systems are designed for a 20-degree delta T, so keep it at 20 degrees, all right? That's going to help. If the boiler is dramatically oversized, it's going to short cycle anyway, right? It's going to short cycle anyway. So that's just the way it is. So there's other factors that play into this, but as far as the pump is concerned, if we can size the pump as close to accurately as possible, will impact that supply return delta T and short cycling. If we're able to adjust the flow rate to maintain a specific delta T as it gets warmer out, we'll be able to impact short cycling. I don't think we're ever going to stop short cycling, but we can certainly help it. Now with a cast iron boiler, delta T, along with widening the boiler's firing differential, is going to really make that thing sing and dance, and that's pretty cool. That's pretty cool. I learned that from Anthony Reichow as well, who's one of the smartest people I know. All righty. Example of a good constant pressure application. Zone valves. So if you're going to do zone valves, you either use delta T or constant pressure, one of the two. All right. And again, if it's a smaller system, there may not be as much benefit going with delta T, so use your constant pressure. It seems to make sense. Okay, you're going to be paying more for a delta T pump, but at that point, is it worth the extra money? Is the additional benefit worth it? Sometimes a bigger system, yeah. Smaller system is not going to be a whole heck of a lot of difference. So if I'm answering your question properly, Benjamin, that's going to be how I would look at it. All righty, couple more. Radiant heat has a 10-degree delta T using outdoor reset, need variable speed pump. Again, never hurts. If it's a zone system, it never hurts. You're still trying to figure out where it needs to be. All right. Can I pump this at 44 watts or do I need 85 watts to pump it? That's part of the question you're asking here as well. The system's going to heat either way. If you've got little manifold actuators on your radiant system, okay, that's a zone valve system, right? That's a zone valve system. When they're all open, they got to run. It's got to run faster. When some of them are closed, it runs slower. So same thing, only different there, Stephen. If I understand your question correctly and if I'm answering it correctly, I think that, yeah, there's always a benefit. There's always a benefit for variable speed pumping. It's just a matter of where it is. And if that radiant system is a single zone, okay, again, it's got to find its happy spot. Do I want to pump? Do I want to do this with 85 watts or do I want to do it with 44 watts or 30 or 20 or wherever it happens to land? Okay, that's the question. Okay, so again, and that's a question you can answer. And I think you can probably figure out where we're coming from there. All righty, let's see what else we have. 65% of the year, the smallest zone is 1/4 of the load. Yeah, that's pretty much it. Do you make a Delta T pump with a supply voltage 230 to 250? No, not at this time. Will those be coming out in the future? Very likely. I couldn't give you a time frame though, Daniel. That's not kind of my department, but I'm sure there will be more coming out in the future as we move along. Let's see. Nice mug. Yeah, thank you, Rocky. Buffer tanks, we got that one. No problem. There's no problem wiring these relays, wiring these ECM pumps to switching relays. No problem at all. It's a regular pump. You just wire it in, boom, done. Okay. All the relay does is turn the power on and off to it. So absolutely, yes, absolutely wire them into a standard switching relay, Darren. No problem at all. Would you prefer one ECM circulator pump working with 3 zone valves, or is it better to have three ECM circulator pumps, one for each zone? Hey Zeus, that's a great question, and that's next month's webinar. I'm glad you asked that. That is next month's webinar, and the answer to both of those questions is yes. I'd rather see either one. But we'll talk about that one next month. And actually, this is a great jumping off point, Jesus. Thank you for asking that. Folks, I do appreciate the questions. I do appreciate you guys hanging in there, and I hopefully this was worth it for you. I enjoyed it, and I hope it was good for you too. And it's a great way to start off the year. And by golly, we'll be doing these every month, both residentially with either myself or some of the other guys. We have Dave Holdorf and Rick Mayo, and we may even get some guest lecturers in here to really spread the knowledge. So we'll be doing that. And also, again, make sure if you're in the commercial world, Rich Medeiros and Brett Zerber are going to do a phenomenal series throughout the year on commercial, TACO commercial products and commercial applications. The first one's going to be one near and dear to everybody's heart. How the heck do you size an expansion tank? It's a little bit of math involved, but it's engineering focused. But if you want to know how to do it, by golly, they'll give you a really good overview on that. So thanks a lot, guys. Any questions you have, any suggestions or recommendations, we're always looking for ways to make these better. You're going to get an email from me tomorrow with again, thanking you for being here, along with the link to the recording. Any suggestions, any ideas, any requests for topics, please share those with us. We're happy to do them for you. And as always, we're here to serve you and help you guys, have as much fun out there as you can, and do the best jobs that you can, and anything we can do to help you in those endeavors. We're more than that. That's our job. So with that, I'm going to say thank you all. I really appreciate you all being here. Happy New Year. Have a fantastic rest of January, and I will see you next month. Take care, everybody.